All right, if you've ever felt that sinking feeling of an ELISA optimization just going completely nowhere, then you are in the right place. You know what I'm talking about. You make a tiny bit of progress, and then, bam, you hit a wall. Today, we're going to unlock a much more systematic approach that'll make your process faster, smarter, and way more effective. Honestly, it could save you weeks of time and a ton of resources.
So let's start with the big question. Why does this happen? Why do we get stuck in that loop? Tweaking one little thing at a time, only to feel like we're ending up right back where we started. It's a huge drain on time and morale for sure, but the good news is, it is a solvable problem. Does any of this sound painfully familiar? Your signal looks great, it's going up, but whoops, so is your background, pretty much wiping out any gain you made. Or how about this one? Your assay is absolutely perfect in a clean buffer, but the second you put it in a real-world matrix, it just falls apart. These are the classic roadblocks that plague ELISA optimization, but trust me, you are not alone in this, and there is a much, much better way to go about it.
This cycle of fixing one problem only to create a brand new one is so common it actually has a name, the ELISA optimization loop. It feels like you're making all these changes, but really, you're just running in place. So let's talk about how we can break that loop for good. Okay, so the traditional way, changing one factor at a time, or OFAT. It feels intuitive, right? But it has this massive blind spot. It completely misses how all these different variables interact with each other. On the other hand, design of experiments, or DoE, is built to test combinations on purpose. This lets you uncover those crucial together effects and build a truly solid, robust process right from the very beginning.
So let's dive into this smarter approach. Design of experiments isn't just some fancy statistical tool. It's really a strategy that lets you see the whole picture at once and finally escape that frustrating optimization loop we were just talking about.
And hey, don't let the formal names scare you off. Just think of your ELISA as a machine with a whole bunch of interacting knobs. Antibody concentration, incubation time, wash strength. Well, DoE is just a structured, super efficient way to learn which of those knobs have the biggest effect, and, even more importantly, how turning one knob completely changes how the others work.
So how do we actually put this powerful idea into practice? Well, it's probably more straightforward than you think. Let's walk through the DoE roadmap, specifically for building a better ELISA.
Here it is, a 4-step workflow that can really transform your process. First, we have to define what success actually looks like for our assay. Then, we pick our knobs, the factors we're going to test, and set some boundaries. Next, we run a screening experiment to quickly figure out the few factors that really matter. And finally, we zoom in on those to find a stable, robust operating window. Let's break down each step.
Okay, step 1 is absolutely critical. If your only goal is get the highest signal possible, you're kind of setting a trap for yourself. A useful assay needs balance. So we've got to define good using practical things like the signal-to-blank ratio, the precision between your replicates, and, this one's a big one, how it performs in the actual sample matrix you're going to be using.
But even if you pick all the right success metrics, your experiment can totally fail before it even starts if you don't choose realistic ranges for your factors. I mean, your high and low settings, they need to be different enough to see an effect, but they both have to be plausible. You can't test conditions that you know are just going to completely break the assay.
And here's what those sensible ranges might look like in real life. We're not talking about just taking wild guesses here. These are plausible adjustments based on experience. Comparing 3 washes versus 5, or maybe a 1 to 2 sample dilution versus a 1 to 8. These are the kinds of meaningful but totally realistic differences that are going to give you useful, actionable data.
All right, the experimental heart of DoE is really a 2-phase process. First, we screen, and then we refine. Let's take a look at how these 2 stages work together to get you to a really solid final method as efficiently as possible.
So the screening phase is all about efficiency. You might start out with a list of, say, 8 potential factors, but let's be real, not all of them are going to be important. A screening experiment is designed to quickly cut through the noise and identify the 2 to 5 factors that are the real heavy hitters, so you can stop wasting your time on the ones that just aren't doing much.
This quote right here, it perfectly captures the whole philosophy of DoE. We're not chasing a single fragile best point that only works on a perfect day with a tailwind, no. Instead, we're identifying a stable, reliable region, a whole window of conditions where your assay just performs well, day in and day out, even with those little real-world variations.
And this is exactly why that refinement step is so critical. Come on, we've all seen these classic ELISA trade-offs. You add more washes, and yeah, the background drops, but then you realize you're actually stripping away your true signal. Refinement helps you map out that sweet spot,
that robust region where you get all the benefits without the drawbacks.
So, you've run the experiments, you've crunched the data, and you've found your robust operating region. Awesome! But the job isn't done yet. The final, and you could argue most important step, is to turn all that knowledge into practical, everyday rules for actually running your assay.
Think of this table as your go-to cheat sheet for common ELISA problems. Got high background? Here are the factors to screen first. Is your sensitivity a little weak? Start here. It's a direct link from the problem you're seeing at the bench to a DoE solution that's designed to actually fix it.
Ultimately, the real deliverable from all this work isn't just a bunch of cool-looking plots. It's a smarter, more robust standard operating procedure. Your DoE results tell you exactly which parameters need tight control and which ones have a bit more wiggle room. This lets you write explicit, data-driven ranges right into your method to make it reliable and easy for others to use too. So let's wrap this all up. DoE is a total game changer because it shows you how conditions interact, helping you learn way faster than the old one factor at a time method. You start by screening to find the big levers. Then you refine to discover a stable operating window. And finally, you translate all that awesome learning into clear, practical guardrails for a method that just works.
And that leaves us with one final question for you to think about back in the lab. Take a hard look at your current methods. Are they kind of balanced on a fragile peak, super sensitive to the slightest change? Or are they built on a solid, robust foundation? Thanks for joining me today.